Hello everyone. Today we're going to be learning a little bit about introductory logic. So, logic is a systemic way of thinking that allows us to parse the meanings of sentences and deduce new information from old information. You use logic informally in everyday life, and definitely while doing math, or in this case computer science. For example, if you're working on a circle in your geometry class, we'll call this circle X, and you have two pieces of information. You have that circle X has a radius of 3 units. And you have the second piece, which is that if any circle has a radius r, then its area is pi r squared. Excuse me. Square units. So, putting these two facts together, you can establish the new fact that circle X has an area of 9 pi square units. Well, if you're a little confused, it's because pi r squared, your r is equal to 3, your radius is 3. So, to get your area, you have pi times 3 squared. 3 squared is 9, and you can just rearrange it as 9 pi. And that's how we get the new area. That is you using logic. You have taken two pieces of established information and concluded with a new piece of information. It is important that logic is not just the process of deducing information correctly. This is what we just did. Deduction means taking a set of truths and arriving at new truths based on that information, like what we just did. For example, suppose we were mistaken and circle X actually had a radius of 4, not 3. Then this entire argument right here would be false, and specifically statement 1 is false. And even in this is true, that's definitely true, statement 2. But our conclusion, therefore, that circle X has a radius, or an area of 9 pi square units, even though we have used the logic correctly, we still arrive at a false statement. So we use the logical process correctly, but because our first piece of information was false, our conclusion is false. The distinction between correct logic and correct information is significant because it is often important to follow the consequences of an incorrect assumption. Ideally, we want both our logic and our information to be correct, but the gist is that they are different things. The study of logic usually begins with going over statements. A statement is a sentence or a mathematical expression that is either true or false. You can think of statements as pieces of information that are either correct or incorrect. So, statements are pieces of information we might also apply logic to obtain new information. Here's some example of statements. The ones we just went over. If a circle has radius r, then its area is pi r squared units. Every even number is divisible with 2. 2 belongs to the integers, that's what this means. That z means integers. The square root of 2 does not belong to the integers. The natural numbers is a subset of the integers. The set 0, 1, 2 has 3 elements, sure. And some right triangles are isosceles. Those are all true statements. Don't worry if you're not quite certain about the notation, they're just examples. So here's some false statements. All right triangles are isosceles. That's definitely false. 5 is equal to 2. The square root of 2 does not belong in the real numbers. that the integers is a subset of the natural numbers, or that the set 0, 1, 2 and the intersection of the naturals is the empty set. That's false. You don't gotta worry about all that, but those are just some examples. Now, more importantly, we come to these things. They're called Boolean operators, and or not. Let's start with and. The word and can be used to combine two sentences to form a new statement. For example, R1, the statement R1 is the number 2 is even and the number 3 is odd. We recognize this as a true statement based on our implicit understanding of the meaning of the word and. But we notice that R1 is made up of two simpler statements. P, which is that the number 2 is even, and Q, that the number 3 is odd. And don't worry about all these letters P, Q, R. They're like variables. You can assign these statements whatever variable you would like. We usually use P and Q and R. So the main point is that this compound statement is made up of two smaller statements, P and Q. Had one or both of P and Q been false, then the compound statement R1 would be false. For instance, each one of these following statements is false. R2, which says the number 1 is even and the number 3 is odd. That's definitely a false statement since the number 1 is not even. R3, the number 2 is even and the number 4 is odd. Again, the number 4 is not odd, so we have false, false, false. Because, again, it says the number 2 is odd and the number 3 is even. Both of those are false. So, any two statements, P and Q, that can be combined to form a new statement, P and Q, is false if one of them is false. At least one of them is false. It has to be all true for the statement to be true. And we use this special up arrow symbol to denote the word and. So if you see something like P, up arrow, and then a Q, that means P and Q. P and Q, the statement P and Q is true if both P and Q are true. Otherwise, it is false, and we can summarize this information with a truth table. So let's examine. So the first two columns, P and Q, are just every combination of true and false that we could have. Either they're both true, or P is true and Q is false, or P is false and Q is true, or they're both false. And depending on those circumstances, we get the last column, the P and Q column, which says that if they're both true, then P and Q is true. If P is true and Q is false, then P and Q is false. False true is false, and false false is false. So P and Q is only true if they're both true. Each line is one of the combinations of true and false values. Statements can also be combined using the word or. So we have the following statements: the number 2 is even or the number 3 is odd. Well, the number 1 is even or the number 3 is odd. The number 2 is even or the number 4 is odd. And the number 3 is even or the number 2 is odd. In mathematics, or just logic in general, the assertion P or Q is understood to always mean that one or both of P and Q is true. Thus, statements S1, S2, and S3 are all true while the last one is false. So true, false. Because each of the first three had at least one true statement in there. So, if P and Q are statements, this P down arrow represents the statement P or Q. So P down arrow Q is equal to P or Q. And we have our truth table. Same setup in the first two columns as before, but now we have truth as long as one of P or Q is true. If they're both true, that's even better, but if they're all false, then we get a false. Only if there are no falsities in there. So to conclude, another way of obtaining statements from old ones is by something called the negation. So let's examine. Any statement P, we can form a statement, it is not true that P. For example, consider the statement, the number 2 is even. That's true, sure. By changing and inserting the words that it is not true that, in the beginning, it is not true that the number 2 is even, this is false. We use the tilde symbol, that's that little squiggly mark here, to stand for the words, it is not true that. So the squiggle P means it is not true that P. Or simply we can read it as not P. Unlike the up and down arrows for and or, which combine statements, the squiggle just alters a single statement. Therefore, the truth table just says 2 lines for the value of P. P is true or false, then not P if P is true is false, or if P was false, then not P is true. This is called the negation of P. The negation of a specific statement can be expressed in numerous ways. So now we get to what if we need to fill out our own truth table. This one wants us to fill out the truth table for P or not R. So the first step we want to do is include the columns for each statement, P, Q, or R, whatever we need. So in this we have 2 statements. We have P and R. Then include any negations we might have. In this case, we have the negation of R. And then the compound statement P or not R. So, in the first 2 columns, we just fill out every combination of true and false that we can think of. So either they're both true, both false, or one's true and the other is false. Then for the not R, we're going to negate all of the values in R column. So true becomes false, false becomes true. And then finally, we can figure out this last column. So if I were to call this like column 1, 2, 3, this would actually just end up being the column of 1 or the column of 3. So we don't even, at this point, we don't even really have to look at that second column. And you might not want to, because it'll help you make it a little bit easier. So, since it's an or, it's only false if both statements are false. So we have true, false, that means it's true. True, true is true. False, false is false. And false, true is true. So again, this means P or not R. And we have just established the truth table for P or not R. Now let's try another one. This is not P and Q. So we have our tables for P, or columns for P and Q. And then we have not P. And then the entire compound, not P and Q. So first 2 columns. Oh, let's just make it true, 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 false, false, true, false, false. The not P column is you take all the examples from the first column and flip them. So we have false, false, true, true. And then this one is the not P column, so column 3 and the column 2. So we can ignore the first one. So since it's an and, they must both be true in order for the entire column to be true. So we have true, false, that's false. False, false is false. True, true is true. And false and true is false. You'll see that the and statement definitely has more false than the or statement. Alright, finally, the last one we'll do for today is construct truth tables for the following compound statements: P, or, Q, and R. So let's have our regular statements P, Q, and R. Then we're going to put our first compound statement, which is Q and R. And then the entire thing P, or, Q, and R. Now, for the first three, it's a little bit trickier, but you're still just doing the same thing. Every combination. So how I always start this process is all true, and then I do every combination where there's one false. So R is false, Q could be false, or P could be false. Now I'm going to do every combination where there's two falses and one true. So true, false, 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 true, false, 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 true, and then the one where they're all false. A little bit more tedious, but not too bad. Okay, now for column 4, what that really is just saying Q, and so column 2 and column 3. So let's look at column 2 and 3, and since it's an and, they must both be true. So we have true, false, false, true, false, 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 and false. The only two where we have that both column 2 and column 3 are true is here and here. Finally, the last part, which can be just summarized. It looks like a lot, but all it is column 1 for P, or column 4. So we can even just get rid of these middle two so we aren't tempted to look at them, and just go off of there. Now, since it's an or, all we need is for one of them to be true. So we have true, 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 false, false, and false. And that is it. Hopefully we see how that works, and hopefully it's all reasonably understandable, because it's all just logic.